Welcome to the Pyro EDU course in Introduction to FPGA and CPLD. In this course, we will cover many topics related to FPGAs and CPLDs while also building up experimental circuits for each topic to help you learn by doing, which I find is usually the best way to learn. Let's start with a quick introduction to what FPGAs and CPLDs are, and to do that, we'll look at the two largest FPGA and CPLD companies, Altera and Xilinx. Both of these companies build CPLDs, which are small programmable logic devices that have onboard memory, and both companies also build FPGAs, which are larger programmable logic devices, sometimes having over 1,000 pin connections. Inside of a CPLD, the pins connect to input-output elements that define whether the pin is an input or an output, as well as what type of logic level should be used, like plus 5 volt, plus 3.3 volt, or plus 2.5 volt logic, or LVDS pairs. And then further internally, there are blocks of logic elements which are all interconnected. These logic elements are blank, and we will be using code to tell them if they should be logic gates or logic elements like a timer, multiplexer, or shift register, and how they should be connected together. CPLDs also have a place to store their configuration image so that when they power up, they instantly configure with the hardware image that you programmed onto it last. FPGAs share a similar internal structure as CPLDs, with input and output blocks, as well as internal complex logic blocks. But they also contain specific hardware modules, like blocks of RAM for holding data, and DSP multipliers for doing complex math. FPGAs, unlike CPLDs, do not have onboard memory, so every time they are powered up, they need to be reprogrammed with a configuration image. To build up the FPGA or CPLD images, most companies will have their own software for synthesizing and implementing. Hardware description languages like VHDL and Verilog are used in these programs, like Xilinx's ISE and Vivado, as well as Altera's Quartus 2 program. A common method for loading images onto CPLDs and FPGAs is through a protocol called Jtag. Here you can see two Jtag programmers, one for talking with Altera parts and another for talking with Xilinx parts. In the world of programmed logic, there are actually more than just two players. Aside from Altera and Xilinx, Actel and Cypress Semiconductor also make programmable logic devices in the form of FPGAs and PSOCs. For this course, we'll stick with Altera all the way through. FPGAs and CPLDs are traditionally more expensive than off-the-shelf processor or microcontroller solutions, and so the high horsepower FPGAs are most commonly found in telecommunications equipment at Juniper or Cisco. But with costs coming down in the last 10 years, FPGAs and CPLDs found their way into other markets like test instruments at Rohde & Schwarz and Agilent Technologies. And in the last few years, FPGAs have found their way even into niche areas like mining bitcoins and in high-frequency trading. The low latency, high-speed, application-specific, and all-hardware nature of FPGAs and CPLDs give them an extreme performance edge over a generic processor. In the last three sections of this introduction, we'll explain what content will be presented in this course, the parts list necessary to follow along with and perform the experiments in each lesson, and lastly, we'll cover what expectations you should have of this course as a student. The first lesson of this course is this introduction, where we give an overview of what FPGAs and CPLDs are, and then explain what this course is about. After that, we dive right in by getting everything set up for programming a CPLD in the Hardware Hello World lesson, followed by understanding how to set up input and output ports, and then moving to implementing combinatorial logic. The next three lessons will add a clock input signal to the mix and explore procedural logic, building a counter, and building parallel hardware modules that operate side by side but independently of each other. And in the last three lessons, we'll have some fun, first by building a PWM driver to dim some LEDs, followed by a handheld POV, and the last lesson, we'll take a comparative look at three hardware description languages, VHDL, Verilog, and schematic entry. Each lesson in this course will follow the same structure. First, in introduction, we'll explain the topic and give some background information. Then in the theory section, we will build up a schematic for the topic and then develop the CPLD image using a hardware description language. After that, we will actually build up the circuit and experiment whether it works or not, as well as how well it works. And finally, we'll take a look at how the topic relates to the real world. It might sound like an awful lot, but with our learn by doing approach, you will be able to learn and do it all. No textbooks necessary. In this course, we'll be using a variety of parts during the experiments, so let's go through them all now so that there's no question about what we'll be using and what you need to follow along. The core parts that we'll use in every experiment are a standard breadboard, a jumper wire kit, and an Introduction to FPGA and CPLD Components kit. In addition, we'll also be using this ThinkPad laptop for building our CPLD images, and we'll need a 9-volt battery for powering our circuits. And now, let's go through the specific parts from the Components kit. First, we have a 9-volt battery connector, USB cable, CPLD Jtag programmer, an EPM 3032A CPLD breakout board with Jtag header, a common cathode 7-segment LED display, CD4511 7-segment LED driver, ICM 7555 timer module, 3 tactile push buttons, LM317 variable voltage regulator, 4 different types of resistors, 10 100 ohm, 10 10 kilo ohm, 5 390 ohm, and 5 240 ohm resistors, 8 5mm red LEDs, 3 10 microfarad electrolytic capacitors, and 2 0.1 microfarad ceramic capacitors. Many of these parts can be found at your local electronics store, but some of them are more specialized, so they will be harder to find. This specific components kit can be found for sale at Gadgetory.com, an online electronics shop. The 3 main outcomes that we hope this course provides for every student are: first, that everyone is able to implement a CPLD project from beginning to end; second, that each student understands the connection between how VHDL code uses hardware inputs to drive hardware outputs; and third, that every student understands how we are not programmers, but that we are hardware designers implementing hardware using code, which is very different from Java, C++, or .NET programming.
All parts in this online course were provided by the Gadgetory. Visit them at gadgetory.com/pyroedu.
Now that you've been introduced to FPGA and CPLD, it's time to take your first step with using a CPLD in what I like to call the hardware hello world. So when you're ready, continue on to lesson 2.